I'm going to talk about the Hilbert transform, which is useful in modulation purposes. So let me explain the properties of Hilbert transform and then maybe an application and how to generate a Hilbert transform of a signal. So you have a signal ft. First of all, the Fourier transform capital F omega is defined as through this linear operation ft e raised to minus j omega t dt. So this relation is interesting. So this is in another domain we call the frequency domain, whatever is the wherever it exists. So if it's only non-zero in a region, then we call this signal to be band limited to some bandwidth b naught. So an important property is that the energy under the signal, which is this in the time domain, also can be related to in this manner with the frequency domain transform expression. So this gives an idea that whatever you see here must be the energy, because this is the total energy. Either you can write in the time domain or frequency domain. So whatever you see here from omega 1 to omega 2 must be the energy content. So if there is a region where it goes to zero, then there is no energy there. And if there is a region where it goes up, then a lot of energy here, etc. So that it shows which part of the bandwidth is region is important in the frequency domain, and this is a basic relation. Now, the Hilbert transform is I'm going to introduce using this crazy function, sine omega function. Sine omega goes like this. And so, as the name says, sine is +1 if omega is positive, and -1 if omega is negative. That means since j is e raised to j pi by 2, we can also write this as e raised to j pi by 2 for omega positive, and e raised to plus j pi by 2 for omega negative. That means whatever is this frequency domain operation, this function, it does a phase shift in this odd manner. For positive frequencies, shifted by pi by 2, otherwise minus pi by 2. So what does it do? So its application is for modulation. You can save bandwidth. That I have already lectured. But so the question is, if you pass a signal ft through this operation, what happens at the output? How do you write this signal? Of course, if this has an impulse response h of t, then f hat of t is ft convolved with h of t. So I'm going to derive the for h of t two different ways, and one is easier, and that will also show you what are the penalties in a Hilbert transform. It has got some good properties, but anytime there is something positive, there is usually some penalty you have to pay for it. So we'll see what this is. This is the convolution operation. So h of omega is many ways you can do this. I'm going to do it one easy way, sine omega. So sine omega is like this. If you take its derivative, you can see there's only an impulse at of value 2. This is the derivative of this function, d by d omega. So if I do a derivative here, that's going to be minus 2j delta of omega. So the question is, remember, what we are interested in is h of t. So if you write down h of omega, you also have this expression. H of omega is h of t e to the power minus j omega t dt by definition. So from here, h prime omega, which is here, is we get that to take the minus j omega minus j t h of t e raised to minus j omega t dt by simply taking the derivative of omega on both the sides. So the inverse transform of this must be this function. So we also have the relation minus jth. A standard relation is the transform of this is h prime omega. In our case, we want to equate this to minus j delta omega. So if you want, here we can cancel minus j, so you get a t h of t. H of t is what we are looking for as a transform of 2 delta omega. So now somehow if you can find the inverse transform of delta omega, then we can equate with this. But notice that one has a transform of delta, or delta t has a transform of 1, because the transform of delta t is delta t raised to minus j omega t dt. That's 1. So using the duality property, one has a transform of 2 pi delta omega. Or from here you can see that delta omega inverse transform is 1 over 2 pi. 1 over 2 pi has a transform of delta omega. So let me substitute it here. So this would mean its inverse transform, IFT, inverse Fourier transform, is 1 over 2 pi. If you go this way, inverse Fourier transform of 2 pi is THT. So from here we can conclude that h of t is, so this is a well-known result, 1 over pi t. So let me just summarize all this. So if h of omega, if you define it to be minus j sine omega in the frequency domain in this manner, at least the time domain expression is more sane. So this is the Fourier transform pair. So this is the Hilbert transform. A Hilbert transform operation. So if I say that I'm going to apply a signal to this filter, which only does Hilbert transform, a convention is you write it as f hat of omega. So f hat of omega is f omega multiplied by h omega. So f hat of omega is f omega multiplied by h omega. And h omega is here minus minus j sine omega. So I'm going to, and if you want, we also have the relation that f hat of t is ft convolved with 1 over pi t. So we can write, this is a well-known relation, but I'm going to create a variation of this which may not be that well-known. Right? So you can, so difficulty is implementing this. So the question is, can we get a second expression for this? So I'm going to start from this expression. F hat of omega is minus j f omega sine omega. So I'm going to rewrite this as j omega f omega and multiplied by minus sine omega over omega. So I multiplied and divided by n omega. And let me write this as j omega f omega multiplied by g of omega. So g of omega is obviously this function. If I do this, so the question is, what is the inverse Fourier transform of g of omega? So somewhere if you look here, so if you look at ft is the inverse Fourier transform of, to find out what this is, f omega. So that's f omega e raised to plus j omega t d omega. Let me take again the same thing, take the derivative on both the sides with respect to t. So there will be a j omega here. So you get, I'm going to put it here. So we can interpret it as the inverse Fourier transform of f prime t as the inverse Fourier transform of j. So f prime t has the transform of j omega f omega. Look at here. We have j omega f omega. So from here we can, and if I call the inverse Fourier transform of this to be g of t, and the inverse Fourier transform of this is f hat of t, which is what I'm looking for. So we have a new relation. F hat of t is the convolution of the inverse Fourier transform of this is, we just found out, f prime of t. So that is f prime t convolved with the g of t. So the only expression that I need to find out is g of t. And then we have a different way of computing this rather than through this expression. Through this expression. So rather than through this expression, f hat of tau is the convolution of ft and 1 over pi t. But this will turn out to be useful. So g omega is, let's keep in mind minus sine omega over omega. So the question is, what is g of t? This we don't know. We have this transform. So I'm going to try my luck and come up with a, let me try this function, L of t or A of t equals 1 over pi log of, natural log of absolute value of t. So A prime t is 1 over pi. Remember, when t positive, log t, the derivative is 1 over t. So for t positive, and t negative, it is log of minus t. So the derivative of that is minus t multiplied by minus 1. So again, it will come out to be 1 over t. So 1 over pi t is the derivative of this function. But this function is familiar. 1 over pi t, we have seen it before. One over pi t is the inverse Fourier transform of that minus j sine omega. So notice it, 1 over pi t has the transform of minus j sine omega. So I'm going to take the transform on both the sides. Fourier transform of A prime t is the Fourier transform of 1 over pi t. But this we know, this is minus j sine omega. From here again, 1 over pi t has the transform of minus j sine omega. And A prime t, we already have it somewhere here. F prime t has a transform of, the derivative function has a transform of j omega f omega. So this is going to be j omega a omega. So we can solve for a omega. J cancels. You get minus sine omega by omega. Notice this is what we were looking for. So these two transforms match. So gt must be the same as at. This is a transform of at. And at is we have here. So this is your gt. So gt is 1 over pi log of absolute value of t. And I'm going to substitute that gt into this expression here. So we have two different ways of doing the Fourier. The f hat of t is also f prime t convolved with 1 over pi log of absolute value of t. So the expression, if you want, this will look like this: f prime tau multiplied by log absolute value of t minus tau d tau. Or you can write it as ft convolved with 1 over pi t, whichever one you want to use. So either 1 or 2. I'm going to use, so to show its application, let's take a pulse from 0 to t, ft. So notice this is a constant modulus, nice waveform, constant modulus. Even if you modulate, it's still going to be constant modulus. So this is what people like in radar and this and that, because it's a uniform power is transmitted. I mean, you can modulate it, it's still constant modulus. But so the question is, what is its f hat of t? Because you need this in to save the bandwidth in single sideband modulation. So this formula is handier, because then if you do this, so its derivative is just 2 impulses, right? So f hat of f prime t is delta t and delta of t minus t with a minus sign. So f prime t is delta t minus delta of t minus t. So I'm going to plug it into this expression. So if you have a pulse of length t Question is, what is its Hilbert transform? So f hat of t is going to be 1 over pi f prime tau log of t minus tau d tau. So that's going to be 1 over pi integral log t minus tau multiplied by two deltas, delta of tau and minus delta of tau minus t d tau. What is the first? So it's going to give you two terms. So this will give you log of t, first term. This will give you minus log of t minus t. So this is 1 over pi log t over t minus t. That's the derivative. So notice when t is 0, this goes to log 0 minus infinity, and when t is capital T, so this will, when t is t equal to capital T, this will blow up to 0, 1 over log infinity, that's infinity. So this function takes a value like this. So you can see the peak power here blows up. This is f hat of t. So this is the one issue with the Hilbert transform. And this is certain, this is constant modulus. So if you take a constant modulus, and if you do Hilbert transform, you lose all that constant modularity. And moreover, this is a finite pulse. This is exists forever. So peak power is large. It actually blows up. So these are the peak power here also. Right? So this is, I mean, you can create other pulses. You get the idea now. So the application, of course, as I mentioned, is if ft has a transform which is band limited. So this is f of omega. If you do ft cos omega naught t, it as a double sideband modulation. You usually this information is the same as the other side, because if the signal is real, these two informations are the same, blue and red. If this is real, you can, by which I mean, you can create the whatever is at minus omega from omega, because f omega is f star of minus omega. So minus omega, if ft is real, so the information at minus omega is just the complex conjugate of f omega. So here you can see that you are wasting bandwidth, because this is whatever is this is twice the bandwidth is used, because the red and blue has the same information. So this is upper sideband and this is the lower sideband, and both of them are identical information. So why transmit it twice? So to avoid this, you can use Hilbert transform. So very quickly, if I write the signal as ft cos omega naught t plus f hat of t sin omega naught t. Then if you do the transform, so we can do it quickly. X omega is the transform of each one of these. So this is f omega plus omega naught plus f omega minus omega naught by 2. Whereas here this is plus 1 over 2j, because sin omega naught is e raised to plus j omega naught t, and e raised to minus j omega naught t by 2. So this is going to be f hat of omega. So notice that ft e raised to j omega naught t with a plus sign, the transform will be ft e raised to minus j omega minus omega naught because t dt. So this is simply the transform evaluated at minus omega naught. So this is omega naught minus f hat of omega plus omega naught. But remember, f hat of omega is minus j. So this is going to be minus j sine omega minus omega naught multiplied by f omega minus omega naught. Then this is going to be plus j sine omega plus omega naught multiplied by f of omega plus omega naught. Notice that j will cancel. So we can, if you write it up, this is going to be f omega plus omega naught. Here you have 1 plus sine omega plus omega naught multiplied by f omega plus omega naught. And then you have f omega minus omega naught, whereas here this will be j cancels, so with a minus sign. So this will come out to be 1 minus sine omega minus omega naught multiplied by f omega minus omega. So you just have to draw the picture and then you will see what it is. So you have, let's start with one. Let's start with this term. So you have, this is f of omega plus omega 0 from here, and then 1 plus sine omega. So sine omega plus omega 0 is like this. That's sine. If you add 1 to that, what is that? This will cancel and you'll only pick up this, which means you pick up this region. So I'll add it here. So you're going to pick up this region. This region is gone. So this is 1 plus sine omega plus omega 0. And now if you bring in the other side omega 0, so you have f omega minus omega 0. So that's like this. This is f omega minus omega 0. Then 1 minus sine. So minus sine would be like this. This is minus sine omega minus omega 0. And if you add 1 to it, this will cancel off. You'll get a value of 2 here. I'm sorry, this will cancel off. So you'll only get this portion. You'll get this portion. You'll get like this. This will be 0. This portion will pick up. Essentially, you're picking up this. So it's going to be, you just pick this up. So the point is now you're only transmitting one sideband, and it has got the same information of the original signal. And if you put the minus sign here, you'll pick up, if you put minus sign here, you'll pick up the upper sideband, which is the other signal. So this is the lower sideband, and upper sideband is outside. This is the upper sideband. So this is x omega, this is y omega, where y of t is ft cos omega naught t minus f hat of t sin omega naught. So what's the point? Point is to generate, so from ft, somehow we need to generate Hilbert transform, and you need to generate f hat of t. So I give you end up with the two formulas. So one way you can generate is ft convolved with 1 over pi t, or this is ft convolved with 1 over pi t, or ft convolved with f prime t convolved with log of t minus tau, f prime t convolved with 1 over pi log natural logarithm of t. So whichever, this is, especially if the signal has edges, this is the one. So you have ft, one way or the other way, create the Hilbert transform. and then multiply by cosine and sine. Add and subtract, you get the two sidebands. So mainly I wanted to talk about if you subtract, then you get y of t, x of t, or y of t, lowercase or uppercase sideband. So mainly I wanted to talk about this formula, and the implication is Hilbert transform is not a nice operation because constant modulus signals, if the original signal has got edges, it's going to exhibit a large peak power at those places. So I assume if the signal is smooth, Hilbert transform also could be smooth, etc. But you have an abrupt end, like beginning and end, it's going to blow up. So you may want to, so that's why this needs to be approximated by some filters which will approximately do the job and still implementable. That's where the vestigial sideband modulation comes up.